Welcome to the student presentation session on the third day of the symposium for undergraduates in Choudhury and Discovery. So I'm Berke. I'm from Izmir Institute of Technology from Turkey. I'm co-president of the Stack Physics Society. And
my name is Melike Aydemir. I'm from Izmir Institute of Technology, and I'm also co-president Stack Physics Society. Thank you.
As a reminder, our team of organizers will be monitoring the Discord, so tag the Quantum Coalition role with any questions related to the organization of the conference. Additionally, we will share the Discord usernames of the presenters in the chat to discuss later or ask questions between each other. So we had an amazing event until now, and this is the first session for student presentations. Today, there will be 5 groups from Princeton, Yale, University of Maryland, and University of Texas Austin with us. So we are starting presentations with Inci Karaaslan from Princeton. And the title of the presentation is Finding a Protected Operational Point for the Generalized Flux Qubits composed of Superconducting Nonlinear Asymmetric Inductive Elements. So stage is yours, Inci.
Thank you for the warm welcome, Berke. So let's get into it. So you guys have already seen what is quantum computing at this point, but just a general kind of description is quantum computers are computers that utilize quantum phenomena for computations. And we all know this, right? And we all know that like qubit is the smallest part of a quantum computer, but the kind of recent developments in research kind of focus more on the designing of qubit. So there are many different designs of what will be the smallest part of a quantum computer. Most proposals involve basing their qubit design schemes on either the microscopic degrees of freedom, which involve microscopic degrees of freedom of elements or and/or ions, either with transition dipoles of atoms or ions in vacuum, or spin of either electrons or nuclei. But today we will utilize macroscopic degrees of freedom with superconducting qubits. So just a kind of quick recap for like iffy about these concepts. A quantum state of a qubit is complex, basically described with a complex vector between the ground state and an excited state. The block sphere provides a really good geometrical representation of quantum states in general. We have 0 as our ground state and 1 as our excited state, and these kind of allow us to get a probability distribution of the outcomes whenever we do a computation and a measurement of a quantum system. So again, quick concepts. Superposition is the ability of a qubit to be in between both the ground state and the excited state. Entanglement is the quantum state of the phenomena where the quantum state of each qubit or particle, that being, it cannot be described independently of the state of the other. And the coherence can best be described with what is coherent. Well, coherent is when there is no interaction between the state of the qubit and that of the environment. This allows for the preservation of information in the system, but any coupling of the state of the system with the environment surrounding it is called decoherence, and it causes some of the information to leak out from the state via acquiring phases from immediate surroundings. So knowing all of this, why do we utilize different designs? Well, we can either utilize, so these are 5 different designs you see here. We can either use microscopic or macroscopic quantum effects, like I said before. But the advantage of microscopic is that it's isolated from the environment more, given its scale, whereas macroscopic scale quantum effects allow for greater interaction with the environment. And these interactions are important because the interactions we introduce to the system allow us to manipulate that system in the field of quantum information processing, and also allow the system to interact with its surrounding environment. But of course, that also introduces coherence. So there's a trade-off here. Either you get to control the system really well with macroscopic quantum effects, or you get to kind of have a coherent system at all times, but not much control to that system with microscopic degrees of freedom. And so what we decided was we use superconducting circuits, so superconducting loops. And just a quick physics recap on this one, of course, is that in a superconductor, electrons function in pairs when carrying in charge. So these are what is known as Cooper pairs. And in very low temperatures, such as 10 to 20 microkelvins, these Cooper pairs act like bosons. And these bosons in, again, said low temperatures actually are allowed to occupy a single energy level known as the Bose-Einstein condensate. And under low temperatures, they basically behave as a one-dimensional quantized particle with a strong interqubit coupling rate. But of course, it needs further design to prevent against decoherence. So our motivation today is going to be just designing protected qubits from superconducting systems. So what is a protected qubit? We already talked about it, but main noises that we see from the environment, so the main causes of error really are bit flip and phase flip errors. Either bit flip errors are qubit state flipping from 1 to 0, and phase flip error is a qubit state rotating by a certain phase. And these, okay, solved here is kind of like a very strong term. It's actually quote unquote solved, but there are many suggestions as to how these errors can be solved. And a couple of those involve either like seeing the matrix elements of a certain design qubit, and if the matrix elements allow certain if that matrix has elements in which they kind of vanish probabilistically between the transition matrix elements specifically, in that case, it allows for better protection from bit flip errors. And for phase flip errors, if your qubit system is somehow degenerate to near degeneracy, there is a chance that you might be able to solve phase flip errors. So that's what I kind of wanted to say here. So basically what this means is that we want to design a qubit, look at its internal modes and see if if there's any chance for it being degenerate. And the quick terminology thing, if it's degenerate, it means we just have like multiple states having the same energy. So either it's that or it produces matrix elements where some transitions are probabilistically just not available. And transitions, by which I mean transitions between, for example, ground state, first energy level, and in some other cases, multiple, like between higher energy levels. So what are we suggesting here? So what we're suggesting is in Half Lab, in the lab that I was working in throughout this project, there are already some protected qubit designs. And two of the most commonly researched ones are 0-pi, as you can see the picture on the left, and Protamon, which is the picture on the right. So like many other designs for protected qubits, these qubits are really hard to fabricate and control precisely because of the amount of loops it takes to fabricate these systems. So as you can see, there's just like multiple loops here for both of them involving Josephson junctions, additional inductors and capacitors. And in that case, of course, it makes it not only hard to fabricate identically, but also the electromagnetic field causes, especially the magnetic field going through each loop can affect the other one. And so that means it's going to be really hard to control these anyway. So the alternative is to get a single flux loop. And it's not only easier to fabricate, of course, but it's also easier to control. And we call this the generalized flux qubit. And you can see that, so the one on the left is the generalized flux qubit with n number of Josephson junctions tied in series, that is tied parallel to a black sheep Josephson junction, and then we have a capacitor that shunts the entire thing. So when n number of Josephson junctions, when we have n equals 3, so 3 Josephson junctions in series, it's called a superconducting nonlinear asymmetric inductive element, which is SNAIL. So what is a Josephson junction? You guys might have already seen this, but basically two superconductors in proximity causes a supercurrent, which is an electric current without dissipation. That's called the Josephson effect, and it is a macroscopic quantum phenomenon. And Josephson junction is basically a junction that utilizes this, an element that utilizes this, and that allows us to introduce nonlinearity in our energy level as like solutions to our Hamiltonian. So you can see the regular quantum harmonic oscillator in figures A and B of the first image here. And those are just regular quantum harmonic oscillators. There's like same energy between each energy level. But then for C and D, which is just the regular transmon, you can see that we kind of create a computing subspace here because the energy levels between 0 and 1, the energy between 0 and 1 is much less than the energy between 1 and 2. And so there's that nonlinearity. So to kind of introduce a couple of terms before I get to the real part of this research here, the Hamiltonian of the transmon you can see here. So EC is the energy of the capacitor or the charging energy. N is the discretized charge state, basically the solutions to our Hamiltonian for each loop that we're going to have. So there's going to be multiple of these. And G is the offset charge representing the effect of an external energy bias. EJ is the Josephson energy, and phi is just the phase difference across each Josephson junction. So these are a bunch of equations here, I know, but you can definitely ask me more questions about this. I'm kind of running fast just for time. So generalized flux qubit, basically what did I do with the GFQ to understand its modes, to figure out whether it's degenerate or not? Basically, the first thing I did was I wanted to get a lump circuit abstraction. So I wanted to get this circuit on the right, but I wanted to model it as if it's the circuit on the left, much like a transmon. So I got this Hamiltonian here, alpha and beta just being normalization factors, which are very much set in stone. Epsilon is the ratio between the black sheep junction, basically the only junction that's in parallel, and the whole array. So that's the ratio between those two is epsilon. EJI, I is the number which Josephson junction in series it is. And Ni, discretized charge state, like I said. Phi I is the phase across each Josephson junction once again. And big N is just the number of Josephson junctions we have in series without with ignoring the black sheep. So I wanted to get this, I basically created this Hamiltonian in order to get the circuit on the right to act as if it's the circuit on the left. And N equals 3 is a good starting point. I can go into why in questions as well. So this is what I wanted to do. And the second method I did was to actually simulate this using a program called S.Q.U.I.D. And in that case, I didn't use the Hamiltonian itself. It actually has its own symbolic Hamiltonian. But these were the parameters I used. So the B here just indicates that it's black sheep, and all of these are in gigahertz. So first kind of analysis kind of showed that, so these are the energy levels of the two systems. So the first one is the S.Q.U.I.D simulation, and the second one is the lump circuit abstraction energy levels. So basically what we got from computing the Hamiltonian for both of them. And what kind of we realized is that obviously we see no degeneracy here as of yet. There's no degeneracy right now for this one where the Josephson energy was 60 gigahertz. This is for those. And what we see is that it's a good fit for high Josephson energy values. Like the lump circuit abstraction really does work, it seems, for high Josephson energy and at low offset. Here we set the offset to be 0. And then we wanted to look more into it, and I will kind of show this later on, but as we go into lower Josephson energy values, however, the lump circuit abstraction actually does not pick up on the degeneracy that we see. And to talk more about the degeneracy, what we realized was, for one, there's, like I said, there's many discretized charge states, so many solutions to our Hamiltonian we will see. But we realized the first one is significantly more important, like 10 to the 20 order of magnitude more important than the other ones. So we really wanted to go for the first possible response. And we realized that there's actually chunks to this. So depending on the Josephson energy, if it's from 0 gigahertz to 0.25 gigahertz, the energies are actually highly degenerate, where we have three energy levels that are distinct from each other. And then from 0.25 to 2.5, we have four energy levels that are visible to each other. From 2.5 to 7.5 gigahertz Josephson energy, we have actually 5 energy levels that are distinct from each other. But for non-degenerate regime, essentially anything 10.5 and higher, we have we have 6 energy levels that are distinct from each other. So degeneracy certainly depends on the Josephson energy, looking at our design. And this is kind of like a small depiction of how, as we increase the Josephson energy, we kind of get more and more energy levels. It's a nice kind of illustration of that. So let's start with, I guess, looking at the matrix elements, right? Because we wanted to see if certain transition matrix elements actually were probabilistically not available. And it seems like for low EJ, that's actually the case. So in this figure, you can see the top left is for 0.25 gigahertz, the top right is 0.5, and then the bottom left is 2.5, and the bottom right is just straight up 60. So all of these are just models of each possible regime that I illustrated here in the 4 tables. And you can see that for low EJs, we actually have some of the transition levels getting lost. And if you want to look at how they compare to the current protected qubits that we have, we actually do see certain patterns that are similar, but something that was more and more getting important to us was the fact that there was no offset charge. Like, this was only true when the offset charge was 0. And why that is important is something that we investigated further. So according to Alexandra Blaise, Professor Blaise in University of, I should not get this wrong, Sherbrooke, the spectrum of the circuit Hamiltonian is actually very dependent on the ratio between the Josephson energy and the capacitor energy of a circuit. And the offset charge is basically depicts the effect of an external electric field bias. So basically how much a circuit is affected by external factors is described by NG. But NG equals 0, then thus means the qubit is completely affected by environmental noise. And so it makes sense that the pattern changes that much. And we realize that, of course, like as we change our EJ to EC ratio, like as we decrease our EJ, we change our EJ to EC ratio. And so the spectrum of the circuit Hamiltonian and the offset charge changes significantly. We can't ignore, like the only way we can ignore the offset charge effect is when that ratio is significantly higher than 1. But at very highly degenerate regimes that I was describing earlier, we actually see that it's very much comparable and sometimes less than 1. So then we wanted to investigate the effect of NG here. And what we realized, so this is for NG equals, so the top left is NG equals, I believe, 0.5, and then NG equals 0.75, and then NG equals 1 on the bottom left, and then NG equals 1.25 on the bottom right. And so you can see that there's, again, a certain pattern going on, but the pattern is significantly different. Their diagonal entries largely appear to be more prominent than transitions between the 2 different energy levels, unless there's, as you can see, this certain pattern, NG is a factor of 0.25. The matrix elements almost seem to be grouped in 2s, where the other transitions are small, and higher, as we go higher in Josephson energy values, all transitions become almost equal in magnitude, or I guess in this case, probability. So we wanted to set the ratio EJ to EC, i.e. the offset charge, to be really high this time, like 50, which is usually the convention in the literature anyway, to see what would happen. And of course, now we see completely diagonal. But we realized there's some subtleties to this diagonal. Just wrapping up really quick. I realized I was running out of time. There's some subtleties to this diagonal, because when we look at 0 pi qubit, actually, we see that there is actually the small kind of, I don't know if you could see this really well, but the more faint probabilities that we see in the transition elements seem to match more to the 0 pi qubit, more than it was before, certainly. So actually, this is really promising in that case, because now we get to try different parameter regimes, which go into different energy modes with varying degeneracies. We want to see that we want to find out, or we have, like, basically, to wrap it up, our conclusion is that the offset charge NG equaling 0 is still a viable candidate for a protected qubit, but obviously NG equals 0 suffers from a lot of the environmental noise that we were trying to prevent in the first place. However, like, this is what we found out, but we also realized that it is with changing offset value to a really high value, essentially trying to protect it from environmental factors, we actually get still a very promising, very similar to 0 pi qubit kind of protected qubit. But the patterns are certainly very different. But in both cases, it seems like an interesting potential to look into, and we want to look into n equals 4 and 5. But they are known to be spectrally equivalent, so we are expecting similar things, but we will look into further the similarities between protected qubits and SNAIL, and which protected qubits, of course, it is similar to. Thank you.
Okay, thanks for this great presentation, Inci. We can take the questions from Discord. We will share the Discord name of the Inci in the chat. So our next presenters from from Yale University, Pranet Sharma, Regine, Mason Abrell, Nikita Mazatov, and they will be presenting an overview of modern quantum architecture. So guys, feel free to share your screen.
Absolutely. Hey, everyone.
Hi.
One moment. All right. Can everyone see that? We good?
Yes.
Yep. Awesome. Well, welcome to the presentation, everyone. We're so glad to have you, and we're excited to get going. So we're going to be talking about modern quantum architecture. My name is Pranet Sharma.
And my name is Mason Abrell.
Cool. So let's briefly overview what we'll be discussing today. So we'll be starting off with what quantum architecture really is. Essentially, how do you structure practical applications of the incredible theoretical breakthroughs that came in the latter half of the 20th century?
And then we'll be going over some of the core technologies that these architectures are based on, specifically the three core technologies of superconducting qubits, trapped ion computing, and neutral atom computing.
We'll then be talking about challenges that these modern architecture techniques face, where we see issues and where we can potentially alleviate them.
Finally, we'll be talking about scaling these systems up to sizes where they can solve many of the problems that we want to give quantum computers in the future.
And we'd like to thank the Yale Undergraduate Quantum Computing Group for helping organize this conference, as well as the Yale Quantum Institute for making all of this possible. We love these groups, and if you are unfamiliar with them, we highly recommend you check them out. Great people.
Definitely. So let's get started. So first of all, the basics of quantum architecture. What is quantum architecture? Well, basically, computer architecture is concerned with balancing the performance, efficiency, cost, and reliability of a computer system and how you can give it commands. So taking that to a quantum level, for a quantum computer, it essentially entails how you organize your quantum system to most efficiently and scalably carry out the instruction sets that you want to give it. So, for example, if I want to ask my computer what 1 + 1 is, the goal of a good quantum architecture is to perform that instruction set as quickly, efficiently, and scalably as possible. So why is that so important? Well, recently, in the past couple decades, there's been a massive increase in the volume of theoretical breakthroughs in quantum computing. You can just see by the number of papers published every year that it's been vastly increasing over the past couple decades. And so these papers contain scientific breakthroughs which could revolutionize the field and push the commercial and common use of quantum computing closer to reality. However, this train of thought runs into one of the most common roadblocks of any scientific field, in that it's difficult to take those breakthroughs and apply them to a wider industrial market, so that its benefits aren't solely contained to the academic arena. But first and foremost, that requires us to implement these breakthroughs into our quantum architecture and even innovate our quantum architecture itself in order to resolve roadblocks in quantum computing. For example, we have to take papers like this and implement it into actual architecture. This specifically is on automated quantum error mitigation, quantum correction. But we need to be able to take these systems and incorporate them into already existing architectures. Or if we need to, design new architectures to take advantage of these novel technologies and novel developments. But moving on, let's just do a quick overview of what a modern quantum computer looks like and how it's structured. So if you look on the at these schematics, you can see at the top level we have quantum algorithms. So that's what the user is inputting in, what commands they're putting in. For example, they might be using Shor's or Grover's algorithms, or doing some quantum simulations to find, lowest energy states. Whatever it may be, the user inputs their request, and then it goes through logical logical steps and interacts with the quantum error correcting system, whatever that may be, the specific system. And then we'll eventually get down to the physical level where you're actually interacting with, the physical qubits or, neutral atom, whatever you're working with. And then once you have your results from your computing, it'll go all the way back up to the user level. So I'm going to hand it off to Pranet.
Awesome. Thank you, Mason. So let's talk a little bit about that bottom layer. That's what people are most excited about. How do we design quantum processors? So there's three main technologies we use, and these are superconducting circuits, trapped ion qubits, and neutral atom qubits. So the past presenter talked at length about superconducting circuits. Very awesome project. Loved hearing about it. So we're going to review it very briefly over the next couple of slides, but they essentially use quantum dots, Josephson junctions in order to facilitate these qubit interactions. And this technology is used a lot by IBM and Google in their quantum architectures. Next, we have trapped ion qubits, which use quadrupole traps and lasers. Very cool stuff. And this is used by two very rapidly growing startups in the quantum space, Quantinuum and IonQ. And lastly, you have neutral atom qubits, which use atom energy levels and microwaves in order to control states of qubits. And these are used by two startups, Quera and Pascal, also within the quantum space. So talking about superconducting qubits, they are basically based on these hardware components called transmons, which create Josephson junctions. So you can see in the image on the left, the square kind of components are these transmons. And the general way that these work is because they're superconducting, they allow for very efficient free flow of electrons. So based on the density of electrons on the junction, which we call Cooper pairs, you can determine what the state is. And as you can see, there's a very clear benefit to the system, right? It looks very much like an existing computer chip, like a classical computer chip. And when you're talking about scalability and you want to make things bigger, when you start with something so efficient, so small, it's very easy to make things bigger. Now, there is a catch here, and that is they are superconducting, which means that you need everything to be at a very, very low temperature. So that's where the dilution refrigeration comes in, which is the image on the right. And this means that even though you have this really kind of this really constrained chip, you may need a lot more infrastructure to actually run it. So this is definitely an engineering problem that will be tackled in the future. So next we have trapped ion qubits. And these use essentially what we call ion traps, or you use magnetic fields to create this little well of potential. And in the very middle, you have an ion, typically ytterbium or rubidium. And you use laser cooling technology to kind of manipulate the energy levels of the ions, which then determines what the state of the qubit is. And then you determine the readout of your qubit, or finding out what state it is, based on whatever photon that it's emitting. And you can read that and kind of tell what state it's in. Now, one big thing to know is that trapped ion qubits have to be moved around physically in order to have interactions. So this is one of the places where there's a lot of work going on to make this more efficient. And lastly, we have neutral atom qubits, which essentially dispose of the ion and only do atoms that are neutrally charged. They are often trapped optically or magnetically, and you use lasers to kind of record the state of the qubit depending on the energy level. And they're typically organized in these lattice formations of intersecting magnetic fields. Now, these two technologies might seem really similar, but some of the biggest differences between them is that neutral atom qubits have much stronger interactions than trapped ion qubits, while trapped ion qubits typically have longer lifespans than neutral atom qubits. And this kind of goes into the comparison between all three technologies. So if you look at this table, this is kind of where the whole world stands right now on quantum computers. And everywhere you see a cross, there is so much work going on to make that a tick mark. So with superconducting qubits, they don't have very long coherence times, which means the qubits very easily kind of collapse. They don't stay alive too long to do more operations, which means that you can't really do it for too long too scalably. But very recently, they just doubled their coherence times, I think in around March, in a team led by Yale and Google, which is super, super exciting. So you can see that this technology, this figure itself is going to be obsolete in a few years because these technologies are being developed so fast. So you can see that even though scalability might be a current issue for trapped ion and neutral atom qubits, in the future, we're hoping it won't be. Now, we've talked a lot about the technologies, but what problems do we face in implementing them? So some of the challenges in modern quantum architecture, really stems from this idea that with a lot of power comes a lot of problems, quoting Uncle Ben kind of slightly, if Uncle Ben was a quantum physicist. So let's talk first about gate fidelity. So gate fidelity is essentially the idea that no matter how beautiful something is theoretically, you're not always going to perfectly implement it physically. So quantum architecture implementations will always have an error, right? Gates may not always perform the way that you want them to perform. So gate fidelity measures how close are you to performing how well you need to perform? Where is that margin of error? Now, there's a really cool way that we quantify gate fidelity or quantum error in general, and this is called randomized benchmarking. And it relies on this really cool technique called randomly drawing unitaries from the Clifford group. Now, the mathematical Clifford group has a few really cool properties. First, it's universal, which means you can use gates drawn from the Clifford group to kind of represent almost anything that you want to within your quantum algorithm. Secondly, it has an error magnification aspect, which means that whatever small error that may be, using Clifford drawn gates will actually make it bigger, which makes it easier to read. And third, the error within the error scales very reasonably, which means that earlier techniques in randomized benchmarking, such as quantum state tomography or Haar random groups, had this big issue where as you kept going with qubit size, the error within detecting the error also got a lot worse. You don't have this problem with Clifford group due to its mathematical properties. And I definitely encourage you guys to go read up on that. It's so, so cool. So using this technique called randomized benchmarking, drawing random unitaries, running your algorithm, seeing what the results are, you can quantify quantum error. And now that you've quantified it, it's time to get rid of it. So this is where quantum error correction comes into play. So within most architectures, you will have a component for quantum error correction where you will use FPGAs, which are tiny microcontrollers, to go through, remove the error from your quantum system that you've detected using your randomized benchmarking techniques. So for example, some of the most common QEC codes modern day use redundancy, or they'll kind of duplicate the measure, see where the errors are by comparing the two kind of duplicated values, and then they isolate the error. And then you can use partial state collapse, which essentially means you only collapse a part of the state, not the entire state, to get rid of the error. And it's really, really cool kind of surgical technique in the quantum world where you're able to very effectively remove the error from the system. And then, of course, randomized benchmarking can be used again to check up on it. Now, we've talked a lot about how things work within the quantum processor, but how does a quantum processor communicate with the outside world? That's where quantum memory management is so important. You know, we now know how things work on one level. How do they work on the broader level? So by kind of making it faster to communicate with the outside world and with data and with getting results out, you can make things a lot more efficient. And that's what this entire field of research is into. How can we make this communication better in order to remove bottlenecks from our system? So if you return to this diagram, you can kind of see a more top-down view. We've talked about kind of challenges in algorithms, challenges in the processors, challenges in the whole communication, but we've also talked about potential ways to alleviate them. And these ways are going to be very important in the next section. Over to you, Mason.
So finally, we have this like really cool system. We have these problems that we're working on, and hopefully we'll have some solutions to them coming soon. But we need to with these like problems, we need to solve them in order to scale these quantum systems, because a lot of the applications of these quantum computers are only useful at scale. For example, some of the applications, as I'm sure most of you already know, are drug development, where you model molecules in order to design purpose-specific drugs or work with genomics, or financial modeling. Recently, firms like JP Morgan have been heavily investing in quantum computing programs in order to generate the next generation of financial modeling systems, or optimization using lowest energy state type solutions in order to optimize trade, air travel, and pretty much anything in between. But the common factor between all of these applications are that they require quantum computers to work at scale and in more strenuous environments than in a lab in a basement. So all that comes back to scalability. One of the first things that you need to have when you're trying to scale a system is a reliable testing platform. So in the past, and in most industries and most fields, there is a pretty clear divide between industry research and government research historically. On the left, you can see an IBM lab, and on the far right, you can see Lawrence Berkeley National Laboratory and some of their work on quantum computing. The issue is that each of these two groups tend to work very hard and come up with lots of a variety of scientific breakthroughs. However, there hasn't historically been a lot of communication between the two and collaboration. But recently, there have been a kind of growth of more hybrid testing environments where you have, for example, Lawrence Berkeley's Advanced Quantum Testbed, where they have a 200-qubit quantum computer that is used by a variety of organizations, both in government and outside government, to test novel quantum architectures. For example, a small startup can apply to use the Advanced Quantum Testbed in order to run their new architecture. And in doing so, they'll probably interact with a variety of other companies, startups, organizations that can help them refine that architecture and can help advance quantum architecture as an entire field. But beyond just testing platforms, there are a variety of future architectures that could help make quantum computing more scalable. One of the most promising is modular architecture, where you have discrete small quantum computers that can be linked together to kind of simulate a much larger quantum computer. MIT has recently been working on this, but the benefit of a modular architecture is that you can kind of scale your system to your need, to whatever specific problem you're trying to ask the system. You can use just as many qubits as you want, or move some if you don't need as many in order to make the system smaller. So that kind of modularity, and in addition, the ease of replacing a system if it breaks, or, you know, constructing a whole new system, kind of gives a modular architecture a very like high scalability, which makes it very attractive. Another future architecture is quantum annealers, which is essentially an approach to solving optimization problems or similar problems that require a like easiest path type question by just using the basic physics behind, or not so basic, but the physics behind a quantum computer, which essentially you have an easy way of finding a lowest energy state. So you kind of take advantage of that natural way in order to solve really complex optimization problems. Finally, there's been a lot of talk and developments in using AI to streamline quantum computing architectures, especially with things like quantum error correction in taking the results of whatever your quantum error correcting code does or says and using it to actually correct your results, and using it just in a variety of processes to kind of streamline your architecture and get rid of a lot of the dead weight that's caused when you do so manually. But regardless, no matter what architecture we end up using, the future is bright for quantum architecture. So thank you, and please let us know. Yeah, ask us any questions.
Feel free to message us on Discord at any point. Our tags are in the chat.
It was a really nice presentation. Thank you. Let me check the chats for questions. I guess there is no question. No, yeah. Thank you. The next presenter is Mark Levin from University of Maryland with equal superposition of n states.
Yes. Yeah. Okay, can you see my screen?
Yes.
Okay. Hi, my name is Mark Levin, and I'm going to be presenting an algorithm for an equal superposition of any n states. First, what is an equal superposition? A superposition is when a qubit or a system of qubits is in a linear combination of more than one state. The probability that a given state will be observed when the system is collapsed is determined by the magnitude of that state in the superposition. An equal superposition is when the magnitude of all states in the superposition is equal, and thus when it is collapsed, the probability of each state being observed is the same. The traditional way of creating an equal superposition is using Hadamard gates. A Hadamard gate puts a single qubit into an equal superposition of 0 and 1. When applied to multiple qubits, it puts the system into a superposition of 2 to the k states, where k is the number of qubits. Many search algorithms use an equal superposition to initialize their search space. However, many of these search algorithms have search spaces that are not powers of 2, and this means that they have to round up their search space. I call this additional search space the auxiliary search space, and it is known that an answer cannot exist in it. So when this auxiliary search space exists, it introduces an inefficiency and will increase the time needed to compute the correct answer. One way that we can remove this auxiliary search space is by creating a smaller superposition of exactly n states. That is exactly what this algorithm accomplishes. These circuits the circuit for n equals 5 and n equals 6 were generated by my algorithm. As you can see, they're a bit more complex than just using Hadamard gates, but I believe that the benefit of removing the auxiliary search space outweighs the detriment of this small added complexity. Additionally, most of the gates that have been added are single qubit gates that can be made very simply with basic gates. As I mentioned, this algorithm works for any given n. This is the circuit for n equals 19, which is a particularly interesting one. You may have noticed that the form of all of these circuits follows a specific shape, which is an arc from the circuit, from the qubit in the circuit of largest magnitude up to the qubit of lowest magnitude, and then back down to the qubit of highest magnitude. I will explain why this is and how this algorithm works by walking through how it generates the circuit for n equals 7. We begin with an empty circuit. With this circuit, all of our qubits are in the 0 state. We first move 3/7 of the probability distribution from qubit 2 being 0 to qubit 2 being 1. We are able to move specific portions of the probability distribution by changing the specific angle of the RZ gates. Conditioned on qubit 2 being 1, we then move 1/3 of the probability distribution from Q1 being 0 to Q1 being 1. We have now completed the upwards portion of our arc. In doing so, we have gone in steps to generate the largest element of our 7-element superposition, that being 7. We will now begin the downward portion of our arc, during which we will backfill all the remaining parts of our superposition. First, conditioned on qubit 1 being 0, we move half of the probability distribution from qubit 0 being 0 to qubit 0 being 1. And finally, conditioned on qubit 2 being 0, we move half the probability distribution from qubit 1 being 0 to qubit 1 being 1. We have now completed our arc, and you can see that we also have an equal superposition of exactly 7 states. It is also important to note that all of the graphs that I'm showing you have actually been generated using a state vector simulator that was input the circuit that is shown together with them. It is not always necessary for the circuit to have a full arc from the qubit of highest magnitude to the qubit of lowest magnitude. In cases where where n is a multiple of some power of 2, some of the qubits will only need Hadamard gates. For example, in the case of n equals 28, 28 is the product of 4 and 7. Because 4 is 2 squared, the first 2 qubits will only need Hadamard gates, while the last 3 qubits will simply have the same arc as was present on the circuit for n equals 7. After all this talk, this allows us to reduce the number of single qubit gates, but more importantly, it also allows us to reduce the number of 2 qubit gates, which are known to be inefficient, and it is best to reduce the number of them. Specifically, this algorithm, this formula shows the number of 2 qubit gates that are required for a given number n. It's a little intimidating to look at, but I assure you it is an O of log base 2 of n. Specifically, the number of 2 qubit gates required is always less than or equal to 2 log base 2 of n, and it is usually significantly lower. The only other way that I was able to find besides my algorithm to remove the auxiliary search space was using a modified quantum Fourier transform with an nth root of unity. However, when n is not a power of 2, these circuits still appear to be hypothetical. And additionally, due to the structure of the quantum Fourier transform, it is likely that they would require significantly more 2 qubit gates than my algorithm does. So after discussing reducing the auxiliary search space, I want to show you an example of how this can actually be leveraged to significantly reduce computational time. One example of an algorithm that can be improved is solutions to a graph coloring problem using Grover's algorithm. A graph coloring problem consists of several nodes which are connected by edges. Each node can be given one of a number of colors. 2 nodes that are connected by an edge cannot be the same color. Classical solutions to this problem are in O of c to the n, where c is the number of colors and n is the number of nodes. This is in exponential time, which means that it's very inefficient. By using Grover's algorithm, we can reduce this to O of C to the n over 2, which, while it is still in polynomial time, is a marked improvement over the classical version. This is an implementation of Grover's algorithm for a graph coloring problem. Specifically, it is for the graph shown on the right, with 3 nodes and 2 edges and 3 colors. The number of qubits required for this implementation of Grover's algorithm for a given graph is the number of nodes multiplied by the ceiling of log base 2 of the number of colors plus the number of edges plus 1. Grover's algorithm consists of 3 parts: an initializer, an oracle, and a diffuser. The initializer is just the equal superpositions initializer that we discussed earlier. The oracle consists of 3 parts, which together accomplish the task of imposing the constraints of the edges on the system. It does this by flipping the magnitude of all states in the superposition that fulfill all of their conditions. It has 3 steps. The first step is computation. In this step, it computes the value of each edge for each value in the superposition for the nodes. Next is the combination step, where it combines the values of all of the edges to flip the value of the ancillary bit. Finally, it decomputes all the edges to disentangle them from the values of the nodes, allowing those qubits to be reused for further repetitions of Grover's algorithm. The third part of the algorithm is the diffuser. This reflects the superposition over the original equal superposition that we began with. Repeating the oracle and diffuser over and over again will gradually move you from the superposition of all possible answers that we started with our initializer towards the equal superposition of just the correct answers. In order to demonstrate how my algorithm modifies Grover's algorithm, I'm going to have to use a slightly smaller example by removing one edge from this graph. The problem with this implementation is that it is not actually an O of C to the n over 2, because C first has to be rounded up to the nearest power of 2, accounting for the auxiliary search space. In order to remove this auxiliary search space, we need to replace all of the Hadamard gates with our initializer for n equals 3. As you can see, the oracle remains the same, but we have replaced the initializer and parts of the diffuser. While this may look like a significant addition to each repetition of Grover's algorithm, remember that most of the gates that have been added are single qubit gates, and the number of 2 qubit gates that have been added is dwarfed by the number of 2 qubit gates that were already there in the oracle and in the unchanged part of the diffuser. So while this does constitute a slight decrease in efficiency of a single iteration of Grover's algorithm, by removing the auxiliary search space, we have significantly reduced the number of iterations of Grover's algorithm that we will have to do. Thus, overall, the efficiency has been improved. These graphs show the average number of repetitions of Grover's algorithm that were needed in order for a correct solution to be observed for line graphs with the given number of colors and the given number of nodes. In cases where the size of the auxiliary search space is very large because the number of colors was very different from the nearest power of 2, namely 5, 6, and 9 colors, we can see that there is a very large improvement from using our modified version of Grover's algorithm. However, in the cases where the auxiliary search space was very small, namely 3 and 7 colors, we see that when the number of nodes is very small, our version is actually less efficient. It is important to remember, however, that in graph coloring problems where the number of nodes is less than or equal to the number of colors, there are trivial solutions to the graph. This means that we really only care about what it looks like when the number of nodes is greater than the number of colors. In the case of 3 colors, we see that when around the place where trivial solutions are eliminated, we see that the modified version of Grover's algorithm is actually more efficient than the unmodified version. With 7 colors, I was not able to simulate more than 7 nodes due to the limitations of the software, of the simulator software. However, we can see that as they approach 7 nodes, the efficiencies of the 2 converge, and it is not unreasonable to assume that they would cross in a similar way to 3 colors. We can see a similar trend in the efficiencies of the 2 versions with more than 9 colors. Again, due to the limitations of the simulator, I was not able to simulate more than 4 nodes for each of these numbers of colors. However, you can see that as the difference between n and 2 to the k grows with a decreasing number of colors, the increase in efficiency by modifying Grover's algorithm in this way increases. Additionally, just as before, as the number of nodes increases, the difference in efficiency also increases exponentially. So it is clear from this graph that in this specific application of Grover's algorithm, there is a marked improvement by modifying it using the smaller superposition algorithm. However, I believe that not only can this algorithm be applied to other implementations of Grover's algorithm to solve other problems, but it can also be used to modify other search algorithms to remove their auxiliary search space and increase their computational efficiency. So if any of you can think of other algorithms that can be modified in this way to increase their efficiency, I would love to discuss them.
Thanks for this great presentation, Mark. Is there any
Thank you.
question?
I think there are no questions yet on chat.
Feel free to
Yeah.
unmute yourself and ask questions.
If there are no questions, let's move on other presentation. The fourth presenter is Caden Kacmarynski from Case Western with virtual quantum optics experiments. Hi.
Hello. All right. A little preface to my talk. This talk is educational, so I'm going to go a little bit of an introduction into quantum optics and the quantum optics experiments I'm going to be talking about today. They show us some interesting things about quantum mechanics. It's going to be a demonstration on superposition and entanglement, which are obviously pretty useful things that we use for quantum computing. And I'm using a software that anyone can use, and you can conduct them virtually. So before we get into the details, what is optics, classical optics? Well, optics is the study of light, and we know that light can behave both as a wave and as a particle. And when we found out that light has particle-like behavior, they're really like little wave packets called quanta of light, which we now know as photons. So quantum optics, well, that's the study of those quanta of light, or photons. So right here on the right, we have an example of what an optics bench would look like. I mean, you're going to see something like this, basically classically or quantumly. You have this optics bench here where you can screw in all your components, and then you have a laser and mirrors, lenses, polarizers, and detectors, or something of that sort attached to the table. And then Okay, and then, so why are we interested in quantum optics? Well, in the terms of this presentation, we're interested in quantum optics because they can show us some things about quantum mechanics. But additionally, for this conference, quantum communication, information, and quantum computation can be affected by quantum optics. And for quantum optics, we need a single photon source. And for my presentation, I'm going to discuss two different types of ways to get photons. The first one will be an attenuated laser, and the second one will be using down conversion. So here's the software that we're going to be using, or that I'm going to be explaining, and it's called the Virtual Quantum Optics Laboratory, or VQOL. And this software is from the Applied Research Laboratories from the University of Texas at Austin. And it's a web-based software. You can just look it up. They have a really useful paper titled VQOL that goes into all the details. It's super easy to use. You see here, you have this like checkerboard pattern, and that's supposed to be similar to the optics table we saw. And then each of the components you can drop into their own squares. And how this works is that each component has a matrix, and that is associated with what would the probability that light would go a certain direction or behave a certain way as it passes through each of those components. So that's kind of how the simulation works. So here's a basic setup of an experiment. So I've dragged onto here a laser and a filter. But here on the right, there's just kind of a list of components that you could use in the software. And it's pretty simple. You can just click and drag and hit play. So if we're running an experiment, it will give you an example here of what's going on. And it's cool because you have a polarization key here. And so you can see a single polarization of light coming out as horizontal from the laser. And then this is it's a neutral density filter. So it's what we're going to be used to attenuating the laser. And then you see this like rainbow colored light here. And that is kind of what this software uses to represent quantum light. So that's what we're going to say. If you see this rainbow light, that's when we're saying we're in the quantum regime. And also in the paper, it describes that. So the solid colors are polarization, but these kind of speckled colors, that you can actually relate those to rotations on a Bloch sphere that they've mapped out in the paper. So it's kind of interesting as well. And then on the right over here, you see like stats. That's what you get after running a quantum experiment. So it basically gives you your shots and your coincidence counts, which we'll talk more about soon. So then furthermore, more usefully is a text editor. So instead of just clicking and dragging, which you have the option to do, you can also just write out your components. So this simple experiment I have here on the right is represented on the left in text. So you can very quickly set up experiments, or you can save a text file and import it into the software, and it will instantly load your experiment. So the first experiment I'm going to be discussing is the Mach-Zehnder interferometer. First, we're going to look at it classically, and then we'll talk about it quantumly. And this explores the wave nature of light with interference. So what you have here is you have a laser, and the laser shoots the light into a 50-50 beam splitter, and the light will then have a 50% chance of going this way. Well, not 50% chance here, it's really half of the light will split each direction and then come back and combine into this beam splitter. But as the light recombines into this beam splitter, it's interfering with itself, and actually all of the light goes to a single detector instead of half and half again. So we can see that here. So what's happening is the red laser has passed through the beam splitter and then hit the mirrors and then recombines at the second beam splitter. And we're seeing that, so this laser here is turned at 1 watt, and the whole watt of light is entering into just this top detector. So we're seeing 1 watt here and 0 watts on the bottom. So what this is showing us is that we're having light interfere with itself, and that's causing this pattern that we're seeing when it's being detected. And what these two new components are is this blue component on the left, that is a wave plate, and the triangle with the box on top on the right, that is a phase delay. So the wave plate can change the polarization of the light. So what we're going to do is vary this experiment at 0, 15, 30, and 45 degrees of polarization just for that top path. And the phase delay can either be 0 or 180 degrees is how I set it up. And so here's an example of when the half wave plate is at 45 degrees. So you're seeing the polarization change here. So you have the horizontal polarization entering the beam splitter, and the top path that the light was able to take, where half of the light split, you're seeing that it is not horizontal anymore. It changes polarization to vertical from the half wave plate. So now, instead of when the light interferes, we get these interference patterns. And now with two different polarizations of light, we're getting actually 50-50, where we're having half a watt going to each detector. So following that out into multiple iterations, this is the graph that we get. So here on the right, we have the half wave plate degrees on the x-axis, and we have the power detected just in detector 1, which was the top detector. So the detection detector 2 is inverse of that because they add up to 100%, or well, 1 watt in this case. And then, so the ideal predictions is this cosine-like behavior, which I have modeled here. And we can see that the blue line and dots are when we have no phase delay, and the red line and dots are when we have a phase delay of 180 degrees. And it makes sense that It's just flipped over the other one because 180 degrees of cosine of 180 degrees is just -1. So it inverses over. And we can see here that they follow exactly along the predicted path. And that's to be expected. Another thing to mention about this software that's really interesting and kind of makes it unique from other simulation softwares is that it can introduce error, specifically for quantum experiments. So we'll discuss that here with the quantum Mach-Zehnder interferometer. So now, quantumly, we're going to be looking at the particle-like behavior of light. So now you may be wondering, if you've never seen this before, well, if the photons follow the same path, are they going to do the same thing? So now what's going to be happening is the light will be coming out of the laser, and it hits this neutral density filter. And so let me see. Now we have a photon entering, a single photon instead of a whole beam of photons. And so now when we switch from classical to quantum, we start talking about probability and statistics, because we're only sending one photon at a time, and we have to measure it tons of times to see what happens. So now with a single photon passing through, it has a 50% chance of following through the bottom path, and then at the same time, a 50% chance of following through the top path. But if only one photon is allowed to pass at a time, you would think that in this second beam splitter then, where is my pen? In a second beam splitter then, you would have another 50% chance to go to detector 1 or detector 2. But what actually happens is the photon interferes with itself. So even just with one photon, with no polarization change from this half wave plate, 100%, about 100% of the detections will occur in detector 1. And that is because of superposition. The photon actually takes both paths at the same time, and it interferes with itself. So it's self-interfering. So to look at this behavior, we're going to run the quantum Mach-Zehnder interferometer experiment. And yes, we're going to be looking at the stats and the probability of detection. So into the experiment. And then another thing here that this software is useful for is now, because we're talking about the quantum regime, we have to run things multiple times to get statistics. So what's nice about the software is you can use JavaScript in the text editor and create loops. So it can run multiple experiments at the same time to get you statistics instead of sitting there and waiting and hitting the play button as many times as needed. So here is the example of the loop that I ran. And quickly, what we have here is, so we have the phase delay, the second component. Again, we ran it at either 0 or 180. So that's what this first loop is doing. The second loop is iterating through our half wave plate angles. So again, we're just going to do increments of 15 degrees. And this time we're running it 10 times. And the rest is just the stuff on the board. So getting into the results. So the results here, you can see the same ideal prediction curve as last time. Again, we have the half wave plate on the X, and now on the Y-axis, instead of power and wattage, we have probability of detection. And so what you notice first here is obviously the dots don't, or the points don't exactly line up with the curve, and that is from that introduced error from the simulation of statistics, which is to be expected. And you can see here, what I did was average 10 runs, and the error bars are the variance from the runs. So basically error. And we can see here it correlates pretty well, and it's showing us that there is wave-like behavior even at a particle level. So the photon is in fact having a superposition of both states and interfering with itself. This experiment was originally run with real equipment, and that's what helped us find superposition and self-interference. So on to the second method of getting single photons for experimental purposes, and this is called spontaneous paramic down conversion, or SPDC, or just down conversion. So what's interesting about this way of getting photons is that it's giving us entangled photons. So how this works is you start with a pump laser, which goes into a mirror, bounces off another mirror. You can put some filters or wave plates in here, kind of can vary there. The important part is this down conversion crystal. So how a down conversion crystal works is it's the pump laser passes through the down conversion crystal into a beam block here. And most of the light something like 98, 99% of the light just passes through unaffected by the down conversion crystal. So it goes into this block. But the crystal has, it's like a parabolic crystal that is able to take some of the photons that are interacted and split them, as shown here on the left. So what happens, I guess, spontaneously, is you have the pump photon coming into the crystal, and it interacts with the crystal, and it is split. So what is called a signal and an idler photon. So these together, they make a pair of entangled photons split out of the crystal. And these have half the energy of the first, the pump beam, and half the frequency. Energy and angular momentum are conserved. And so you then have your entangled photons, a signal and an idler photon, coming out of this crystal. Mark Beck's quantum mechanics textbook is a really good resource if you want to read more about this. He just basically explains quantum mechanics, but using experiments like this. So that's cool and all, but how can we set it up in the software? Luckily, in the virtual quantum optics lab, they have a black box that essentially does everything that I just showed you for us. So right here, what they call is their entanglement source is this box that shoots out the signal and idler photons out of the sides. And you can make it go up and down or any of the four angles. And one of the parameters, so each of the components in the software you can click on and you get a little pop-up menu like this, where you can set the position, and each of them have some set of parameters. For the entanglement source, the main parameter here is strength that we're concerned about. And what strength would do is that's basically changing the power of the pump laser going into the down conversion process. So if we have a really, really strong laser, or we're just putting a lot of photons and a lot of light pumped into this crystal, it could be too many photons for quantum mechanical behavior. So we want to look at that strength parameter to see where we get the best behaving light. So this brings us to the photon anti-correlation experiment, which is shown here on the right. And so something that's really important when you're dealing with, well, normally quantum optics experiments in general, but especially if you have entangled pairs, you're going to want to look at coincidence counting. And what coincidence counting means is you're going to look at multiple different detectors at the same time. So here are the detectors, and when the detectors detect a photon, we call that a click. So what we have here from the entanglement source is we have this signal photon going to detector 3 here. At the same time, we have this idler photon going the other direction into a 50-50 beam splitter, and it can have the path of either detector 1 or detector 2. So what coincidence counting would be is we know that, and they're all the same length away. So when the idler photon or the signal photon reaches detector 3, at that exact instance is when we look at detector 1 or detector 2 to see what type of measurement we had. And that would be a coincidence count, meaning they clicked at the same time. And this also means that what we're interested here is the path of the idler photon in the 50-50 beam splitter to detector 1 or detector 2. And detector 3 is then called a heralding detector, because we're using that detector to tell us when we should look at the behavior of detector 1 and detector 2. And I guess to explain why we're interested in the behavior of detector 1 and detector 2, if we have a wave, and the wave, or if it's not a photon, basically, if we don't have a photon, that means we could have some type of wave that would split, and we would get detections in detector 1 and detector 2 at the same time. But if we have a single photon coming out of the entanglement source, that means that at the instance detector 3 has a detection, only detector 1 or detector 2 can have a detection. And if they both have a detection, that's a problem, because that would mean something that we're not expecting is happening. So that's what we're going to look at. So how we look at that is we're going to look if detector 1 and detector 2 are anti-correlated, meaning when there's a detection at the heralding detector, detector 3, we're going to look at the detections percentage of detector 1 and detector 2. And we basically want to show that there shouldn't be detections at the same time. And now, kind of to skip over the math, we end up with an equation here. These ends, the n sub 3 is a count in detector 3, and n sub 1, 2, 3 is a coincident detection of all 3 of them, which in that case, we would expect it to just be like ambient light or light in a room if you're doing the actual experiment. And so the coincidence counts that are really important here are this N13 and N23. Those are those detections we're looking at. And so what we call this is alpha. So here is the graph of the results of looking for this alpha, which we want to be below 1. And so on the x-axis here is that strength parameter from the entanglement source. So you can think of that as how many photons are we pumping into this system, like how strong is the laser. And then on the y-axis is that anti-correlation coefficient. And so we are in the quantum regime if this alpha is below 1. That means we're getting particle-like behavior from the light. And so you can see here that when the laser is really strong, and as we're approaching 1, that it's above the cutoff that we're looking for. So this means we're getting more classically behaving light there. And as we go lower and lower, we're getting a lower and lower anti-correlation coefficient. But what you can see here from the dotted line, which is my variance, we have a very large variance when you get really low. And this makes sense because if we have so few photons that are passing through the system that we're not getting enough statistics to have something accurate, you can have very large variations. So in terms of using the software, we're seeing the best behavior around 0.7 or 0.8 strength. But what we can take away from this, what this means is if we have tons and tons of photons in a system, or like a classical laser, it makes total sense that we're getting classically behaving wave-like nature. And if we have way too few photons to really get enough statistics to understand what's going on, we get this huge variance. So there's this sweet spot in the middle where we're applying enough photons into the system to get enough statistics, but not too many photons where we're not getting quantum behaving light. So this is kind of exploring the behavior of entanglement and how we use it in a lab. So the conclusion of this couple experiments is we're looking at the wave-particle duality of light. We looked at superposition and interference, and then entanglement. This virtual quantum optics lab is pretty accurate and a great tool for simulating optics experiments. Their paper has multiple other experiments, notably like the Bell experiment is pretty famous, and quantum optics is a hands-on way to learn quantum mechanics. Thanks for listening, and is there any questions?
Thanks for this great presentation, Caden. We can take the questions from Discord because we are a little bit out of time. So we are moving on to our next presenter from UTAustin, Karnika Choudhury, Introduction to Quantum Error Correction.
Good morning, everyone. I'm just pulling up my slides now.
Good morning.
Okay, can everyone see my screen?
Yes.
Yes. Okay, I will get started then. Like I said, good morning, or I guess almost afternoon. My name is Karnika Choudhury, and I am an undergraduate student at the University of Texas at Austin studying computer science. Today, I'm going to be talking about quantum error correction. I know some of the other presenters already mentioned it, so if you were wondering more about what that is, that's what my presentation is about. So first, in order to understand why we need quantum error correction specifically, I'm going to be talking about just quantum computing, just a brief introduction. So as a whole, quantum computing is an alternate form of computing to classical computing. And the main difference here is that classical systems work with bits, which can only exist as 0 or 1. But the thing about quantum computing is that we use qubits, and with qubits, we can represent qubits in several different states that are essentially different superpositions and combinations of the 0 and the 1 state. And because there are millions of different states that qubits can exist in, this complicates a lot of aspects of quantum computing, but it also allows for improved performance and capabilities. One of these examples is Peter Shor's algorithm, which shows how a quantum computer can break down a number into its prime factors in polynomial time. This is significantly faster than a classical computing system can do. And there were actually encryption techniques that relied on the fact that classical computers cannot do this quickly. So quantum computing did break a pretty important part of encryption. That is why quantum computing is so powerful and important. And the scientific community greatly anticipates these new capabilities. But as we make these chips bigger and more complex, we get more errors. And that's what my presentation is about. But first, let's go over what an error is. So an error is essentially what happens when external noise or an interfering electrical signal disrupts the transmission of a message. So if we are trying to send one thing from one system to another, we want to make sure that message stays constant. But what can happen is different external signals from the environment, which we call noise, can end up messing with that original message and changing it. And if we cannot maintain consistency between the original and the received message, then this can disrupt algorithms and it'll lead to the failure of a system. So in order to fix this, we have error correction algorithms, which essentially either before or after anticipate the error and correct it, or look at the received message and then correct it to match the original in order to account for like any noise or interference that occurred. So the way this works in classical computing is there is one kind of error, which is called a bit flip. It's just a simple flipping from a 0 to a 1 or a 1 to a 0. And even though it may sound minor, it can lead to extreme failures. Like if we were to launch a rocket into space and if some interfering electrical signal were to make a 0 into a 1, it could cause the failure of the rocket. So although it is a small thing, it still has significant impacts. But the thing about classical computing is the fact that we have transistors. And the thing about transistors and the physics with which they're created is that they enable for a high error margin because of their strict on and off states that essentially eradicate a lot of different failures that can occur. And because we can make things like transistors with classical computing, and when it comes to error correction, we try to take more preventative measures because we can do that. And there are actually error correction algorithms for classical computing that involve repetition codes or elaborate on like Hamming distance. But we're not going to get into that right now. Now, the reason that error correction is a little more strange, I guess, with quantum computing is because of the nature of qubits. But before I discuss that, let's just go into the different kinds of errors that can occur in quantum computing. So we have bit flips, just like in classical computing, 0 and 1, 1 and 0. And then we also have this thing called phase flips, which essentially is the rotation of a qubit into different states. And this is typically like represented as like a sign flip, as from like plus minus or minus to plus. It'll make more sense when I discuss the algorithms later. Now, the main reason that quantum computing error correction is so difficult and it took so long for scientists to completely understand is because of how fragile qubits are and how it can lead to decoherence. And so the issue here is like best represented, I believe, with the concept of observation. When you go to measure the state of a qubit, just to see what state that qubit is, it's possible that it can just completely collapse. And it's really hard to isolate qubits from external noise, which is why we can't really prevent them as well as we can with classical computing. The fragility of qubits also directly ties into the concept of the no cloning theorem. The no cloning theorem states that we cannot perfectly copy the state of a qubit or make arbitrary measurements because of potential wavelength collapse. What we can do in classical computing and the way we do repetition codes there is, let's say the original message is just a 0. We can make that 0 into 0, 0, 0, and that's called the encoding process. And when we encode it, if an error were to occur on one of the qubits, let's say it became from 0, 0, 0, it became 1, 0, 0. Because the other two qubits are 0, and we know we encoded it to have like 3 qubits instead of 1, by a simple majority rule, we can see that an error occurred on the first qubit, we can flip it, and we're done. But since we can't copy states like that in quantum computing, things are a little bit more complex. Now, I mentioned before how powerful quantum computing can be, but many scientists found the fragility of qubits to be a threat to its true potential. However, Peter Shor came up with a different kind of repetition code, where we entangle qubits across a different vector space of qubits, which is called an expanded Hilbert space. So I'm going to be talking about 3 different errors that can occur basically in quantum computing, and 3 different algorithms that can fix those errors. So the first one we're going to be talking about is just correcting single bit flips in quantum computing. So the first step we're going to do is we're going to encode the qubits. Just like in classical computing, we make a 0 into 0, 0, 0. What we can do in quantum computing is we can take that original qubit, and we basically have a lot of literature describes it as 2 ancillary qubits to protect the original. So that can be shown over here. We use C0 gates to do that, where we entangled the original qubit with the first ancillary qubit and the original one with the second ancillary qubit. The original qubit can be in any arbitrary state, whatever message you're trying to send. And the ancillary or auxiliary qubits must start in the 0 state. Okay, then we have this concept of cinder measurement, which is basically just trying to figure out where did this error occur. Yeah, so the syndrome is defined in quantum computing as which qubit the error occurred on, and we want to try to figure that out by measuring the syndrome, hence the name. In order to understand this, we're going to go over a concept called parity. This is also very simple. It's parity is just basically to see if two qubits are like in the same state. In order to exemplify this, I have this little example right here. And the first and second qubit, those have the same parity because it's 0, 1, and 0, 1. So they're in the same state. But if we look at the first and the third qubit, that's 0, 1, and 1, 0. Those are not the same state. So those two qubits would have different parities. So what we do is we essentially check the parity with the ancilla qubits. So once we entangle them, if it's in the 0 state, that means it's the same parity. If it's in the 1 state, that means it's a different parity. And you can kind of see how we do that in this circuit diagram over here. We take the original and we apply C0 gate to the original and the second ancillary, and the second one and the first, and then first. And then basically we're just measuring, it'll be more clear on the second one, but we're looking at the first and the second and the first and the third. And then this sign over here, this is just a measurement. Okay, so now we're on the third step, error identification and correction. We want to figure out what we figured out. We measured which qubit the error is occurring on, and we want to know which qubit that corresponds with. Okay, so over here, I talked about earlier, what Peter Shor said is we take the original qubit and we embed it into an expanded Hilbert space. That's what we're doing here. We've essentially encoded a 2-dimensional Hilbert space spanned by the 0 and 1 state into an 8-dimensional Hilbert space with these different spanning sets over here. These are called logical error code spaces. Now that we've made the parity measurements, we have these register states over here that show us where the error occurred. In order to understand the logic here, let's look at the second row, the second code space spanned by 001 and 110. So if you look again, like with the technique we looked at earlier, if you look at the first and the second qubit, they have the same parity, but the first and the third qubits, they have different parity. Now, if you think about it just logically, if the original qubit was 000, and the first and the second qubit are now the same, but the first and the third qubit are different, then where did the error occur? Which one's different? The third one, because the first and the third are now different. So just by using this logic, we can see that the second row, it is obvious that the third qubit is where the error occurred. Going back to the first row, it's still the encoded qubit still exists in the 000111 spanning set. So that means nothing happened, no error occurred, we're good. The third row here indicates that there was an issue with the second qubit, and the last row suggested there was an issue with the first qubit. And then all we would do at this point is we would have to apply an X gate to the affected qubit in order to correct the state. And one thing I want to note is that in the first and the second algorithm that I'm going to be discussing, I will be talking about it's more of a manual thing where the circuit doesn't automatically correct the error. It just tells us where the error exists. But in the third algorithm, I'm going to be talking a little bit about how we can automatically get those errors corrected. Okay, this is the second one. This is the second type of error we have, and it's correcting for single phase flips. Okay, so this process is actually very similar to bit flips, which I did not know on initial research, but I found it very simple to understand. So what we're going to do is we're going to use 2 ancilla qubits, just like earlier, and C0 gates in order to transfer the original quantum state onto the ancilla qubits. However, the difference here is then we apply these Hadamard gates, and we bring these qubits into superposition. And then this place over here marked E phase, this is where noise occurs. This is like this is just the part of the circuit where we anticipate some like noise or error could occur. And another thing, what we do by applying the Hadamard gate is we take the qubit from the standard computational basis spanned by 0 and 1, and we bring it into the plus minus basis. And I just put these little diagrams over here just as like a reminder. This is what the plus minus basis is, and this is the effect of Hadamard gates on the states. As you can see, it brings 0 into plus, plus to 0, 1 to minus, minus to 1. So that's just what Hadamard gate does in general. So using this, we can, we're back at the syndrome measurement. And after we send the message across, there's of course a chance that a phase flip would occur. This would be seen as a sign changing on the C0 gate. We can convert the state back into the 0-1 basis by applying Hadamard gates again, and this Toffoli gate over here. And the logical qubit is controlled by the 2 ancillary qubits. Now we are back to the computational basis. The area labeled E phase here again is where the noise can occur. And at this point, we're back just how it was with the bit flip error correction code, where we check parity. 0 is the same parity, 1 is different parity. And we would be back to it. We would come back to a vector over here where it's spanned by these different code spaces. This is the same table as we saw before. And the only difference here is we would apply a Z gate to the affected qubit to correct the state. Okay, now we're going to be talking about Shor's 9-qubit quantum error correction algorithm. So this is essentially a code concatenation of bit flips and phase flips. So the two algorithms we discussed before, this is a combination of those. And as long as you use those 9 qubits, you can correct for any error on a single qubit. This means you don't have to know if a bit flip occurred. You don't need to know if a phase flip occurred. It could be both. Any different error on one single qubit, this can correct. Okay, so in the encoding process, we can see that we're using 8 auxiliary qubits instead of 2 before, because the way this is designed, since we don't have to know whether a bit flip or a phase flip occurred, we have to use more qubits in order for this to make sense, and I'll explain that a little bit later. Okay, so here we can see elements of bit flip, which is where we take the 0 and we go 0, 0, 0 and 1, 1, 1. So we have the duplication just like we do in the bit flip error correction code. And we have the embedding into the plus minus basis, which is shown by the plus signs and the minus signs. Okay, before I talk about syndrome extraction, I just want to make it very clear what these errors would look like when it comes to this code. So this is the qubit, the encoded qubit. A potential phase flip error would look like this, where the plus sign would become minus. Or if it was a bit flip error on the second qubit, we'd see the 0 and the 1 would flip. So, okay. Now I talked earlier kind of about syndrome measurement in terms of parities and projecting to code subspaces, and we can still do this with the 9-qubit error correction code. But I'm going to be talking about it in terms of unitary transforms this time, just for something different. So what we can do is we can identify the syndrome by expressing it as a unitary transform as a linear combination of the polygates, where C1, C2, and C3 are complex constants. There are 2 different layers here, where we correct for bit flips in one layer and we correct for phase flips in another layer. Syndrome measurement, another way to think about it, apart from the unitary transform and the parity measurement, is more conceptually, we measure whether we exited the stabilizing state of the original qubit. Now, in order for this to make sense, let's look at the table down here where I have the different qubits and their stabilizers. So let's say we have the qubit 0. We transmit a 0 from one system and we have the receiving system. The receiving system can conceptually check if that qubit is still stabilized by I and Z. If that qubit is still a 0, it should be stabilized by the I and Z gate. If it isn't, then we know that an error occurred. So this is like another way to think about it. So what we're doing here is we measure the change in the qubit, and what we want to see is if that stabilizer still stabilizes that qubit even after we cross the area where noise occurs. Generally, when we have n-qubit code, we have k-qubit message, and we need n-k polystabilizers. Okay, so back to the concept of the unitary transform. If you, when we reduce it, if it's identity matrix, there was no error. If it's the X matrix, bit flip occurred. C matrix, sign flip occurred. Y matrix actually means that both a bit flip and a sign flip occurred. So again, this algorithm can look for that as well. And before, I was talking a lot about, again, like this manual concept of finding the syndrome, and then you go in yourself and you correct it. But obviously, as computer scientists, we want something more automatic so that we don't have to actually put in all that work, because computer scientists are notoriously lazy. So there's also another method, like I found this on IBM's website, and this is kind of how they structure their code for Shor's 9-qubit error correction algorithm. So the way we do this is first we take the computational state of the original qubit and we transfer it onto the 3rd and 6th qubit. And this is assuming that we have original and then 1 through 8 qubits, 1 through 8 ancillary qubits, right? And the 3rd and the 6th, those are going to handle kind of the phase flip part of this error correction. And then we're going to put the 3rd and the 6th qubit into superposition. We then take these superposition states and we transfer them to the respective ancillary qubits. For example, like the main qubit transfers to the 1st and the 2nd. The 3rd qubit state transfers to the 4th and the 5th, and the 6th qubit state transfers to the 7th and the 8th. Once the bit flip, the phase flip, or both occur, whatever happens, Toffoli gates are applied to the main qubit, the 3rd qubit, and the 6th qubit, with their ancillary qubit serving as the control, because Toffoli gates are required to control qubits. So for example, we'd apply like the Toffoli gate to the main one with the 1st and the 2nd as the control. After we do all of this, we're going to bring the third and the sixth qubit out of superposition. And the CNOT gates are applied to the third and sixth qubit, with the main qubit serving as the control in this case. Finally, we're going to apply a Toffoli gate to the main qubit, with the third and the sixth serving as the control. And that's just kind of what's expressed in this diagram over here. As you can see, there's a lot of use of Toffoli gates. And Toffoli gates are really powerful gates. So using them allows us to automatically correct the error. Okay, these are my references. I wanted to thank you guys so much for coming and listening to my talk. I really enjoyed researching this topic. And this presentation was quite literally brought to you by me, my mentor, Ronak Ramachandran at UT, and the whiteboard that he explained a lot of these different concepts to me on. So thank you so much for this opportunity, and I hope you have a great rest of your day.
Thank you for this great presentation. Do we have any questions? Okay. Then I thank you to all the presenters and all the groups. All the presentations was great, and we will see you in section 2 of student presentations at 2 p.m. Eastern time. Thank you, everyone. So see you later.